Today, we are fortunate to invite Dr. John Witter from OSU to talk about conservation ditches. So actually, when they were talking about, mention the conservation ditches, I always wanted to remember one person, Andy Ward, Dr. Andy Ward. He's kind of a mentor, teacher, also a friend to both John, and me. He's actually he's a good researcher. He kind of pioneering the two-seed ditch concept, along with a couple of students, John, Jessica, Anad, G.E. Powell, also Dan Meckenberg have been heavily involved in the development of the spreadsheet tools. So Andy Ward also kind of pioneering conservation as well. And after that, actually, so currently, John has been a leader in this field in the conservation ditches. John is graduate from OSU. He got a PhD in ag engineering. He's not only an outstanding researcher, but also he received numerous kind of reward in teaching. He's also a good teacher. So I think I probably don't need to mention too much because he's already well known in this field. So without further ado, let's welcome John to talk about the conservation ditches. Welcome, John.
Great. Thank you, Chung. I appreciate it. Let me get the presentation going here. Are you able to see my title slide before I get started? Good to go. And Chung, you were mentioning a lot of the people that were involved in the early days, the research, developing the concept. But one of the best collaborators along the whole process has been so many numerous people with the Nature Conservancy who've been involved with implementing this project, helping with the research from the beginning. It's almost going on 2 decades now, going all the way back to Joe Draper in Indiana and Kent Walmsley, to more recently working with Jason Milks down in Arkansas. Yourself, you forgot to mention yourself in the group of researchers that looked at this practice early on, and certainly Jessica, who's probably one of the most knowledgeable people in the world on this practice. So our relationship through Ohio State, through some of the state agencies with the Nature Conservancy, has been a really rewarding partnership. So I'm going to share some more of the recent research. If you're not familiar with the concept, I'm going to go through that a bit today. If you're veterans of some of these meetings on water quality, you've probably seen a lot of things going on in the field and at the edge of the field. And we really look at what are the opportunities to manage or improve water quality after it's left that field. And we think agricultural drainage ditches are a really important piece of infrastructure, not only for ag, but for urban and suburban areas that, are prone to flooding. Those are certainly important features of the landscape. And really, this infrastructure, this important infrastructure requires some maintenance. We have ditch maintenance programs. And so what we look at is it worthy of investment to help upgrade that infrastructure, but also provide some water quality benefits if we invest to do it slightly differently than maybe what we've done historically. So can we provide what the landowners need locally, but then provide also benefits to society in terms of water quality, protection of those water resources? For anybody that's maybe not familiar with Ohio's landscape, it's kind of a mosaic or patchwork of wet landscapes historically prior to settlement, wet sedge meadows, tall grass prairie, forested wetlands, and swamplands. And for public health reasons, many centuries ago, they were drained through a lot of surface drainage, and that revealed some productive land for agriculture. So we started to drain that more intensively, which would have included tile drainage, perforated plastic pipe, mostly 4 inches in diameter with perforations buried beneath there's rolls of it. If you haven't actually seen it installed, you've seen rolls of tile drainage or of tile stacked up in fields, and that's buried roughly 2.5 to maybe 4 feet below the land to remove above field capacity. So all the water that can be drained by gravity will come out through these pipes. And sometimes these pipes are installed systematically. Here is an aerial view of a field that was just tiled. And it used to be the tiles were spaced every, 40 or 50 or 60 feet. But as farms get larger and it's more important to drain those quickly so farmers can get in the field, that spacing has come down to, 20 feet or maybe 15 feet to get that drainage response more quickly. So a lot of pattern systematic tile systems out there. More recently, people are putting those on the contour to try and facilitate drainage water management. So can we control how much water and nutrients are leaving the field by managing the water table? So you see different systems like this becoming a little bit more popular. But in the end, the reason these practices, people, farmers, producers will invest in these is because it's meaningful for crop production. I know this is an older photo, maybe not the best of photos. This was given to me, I believe, by Norm Fauzi or Larry Brown, who work on drainage extensively here in the state. And these two fields, these plots, they were prepared. The tillage was done exactly the same. The planting date was the same. The hybrid was the same. Soil fertility was similar. The fertilization and crop care programs were similar. The one difference being one had improved subsurface drainage and the other did not. So in any given year, you could probably get farmers to argue which is more important, drainage or fertilizer. Really probably depends upon the year, but this is really an important practice for viable agriculture in this state. And all of these extensive tile drainage systems that are buried beneath the fields need an outlet. And that outlet is often in the form of an agricultural ditch that has been constructed by humans so that there's an outlet, a place for that water to go and then to be carried downstream. Unfortunately, a lot of these tile outlets, will bypass a lot of the conservation practices we put on the landscape. So things like buffer strips, tile water, or the discharge of tile water that bypasses those may make up oftentimes 50% or more of the total flow in a stream in a drained landscape. So the trapezoidal ditch has been a pretty standard design for hundreds, if not thousands of years. It's incredibly efficient from a civil engineering standpoint. It does exactly what we want very efficiently. It's easy to construct and it takes up a minimal amount of space. From an ecological engineering standpoint, this design isn't ideal because it's not working with nature. It's we're not really considering what nature wants to do in this case. So we're constantly needing to maintain it. And a lot of times what nature's response to channelization is either through erosion of the bed or bank. And most often in Ohio, it's the banks would fail. So you get a bank failure, it introduces sediment into the flow, or you get a bar developing. It becomes vegetated. And all of a sudden it starts to redirect the flow into the ditch banks. So you get some bank erosion, which the farmer doesn't like because it makes their field an irregular shape and it's easier to farm in straight lines often. So here it's regaining its meander pattern in nature's attempt to renaturalize itself. So that's one response if there's enough energy through erosion of the bed or bank. And the solution for that is if that's happening, I don't know if this was a bank reconstruction problem due to failure, but this is what a bank reconstruction project would look like. They peel back the slopes, restabilize that. Here they've seeded it, put on a straw matting or a straw mulch to try and get that vegetation to reestablish. So at the cost to the landowner. Probably the more common response nature would have to channelization, at least in this part of the world, might be for sedimentation. So silt builds up, it doesn't have enough energy to move that sediment downstream, so it builds up, and all of a sudden it starts to block the tile outlet, and the tile drainage system in the field doesn't work properly. So that would instigate a maintenance activity, what we call ditch dredging or dipping sometimes, or my favorite, cleaning the ditch. And you can see it's all to give those tile outlets highlighted in white there in the white circles to give that outlet so they can function properly again. And oftentimes that spoil, that sediment that's dipped from the ditch is spoiled very closely to the ditch. So it's at risk of the sediment and nutrients getting back in. But it's usually, it's often viewed as a waste. So how do we quickly get rid of it at the least cost possible? And this is one option to do that. So let's look, I talked about conservation ditches, and there's a number of different practices that we hold under that umbrella. And I'm going to give you a couple of those options right now. Here's your traditional trapezoidal ditch. So you had, maybe a wetland stream, or maybe it was just a wet area that was usually hand dug or plowed out by, horses or mules initially hundreds of years ago. And now they're constructed with excavators. You get that very regular trapezoidal shape to give those tiles outlets. So that's your traditional trapezoidal agricultural ditch. In places where our conservationists or engineers designed a ditch that had an adequate width at the bottom, sometimes you get a depositional response. Erosion from the fields gets into the drainage system. They vegetate and they start to build these little small floodplain benches in the bottom. So where they were accidentally given enough width to do that, nature might have created these small floodplains. And essentially what you have is a small meandering stream channel within the bottom of a ditch. So a maintenance activity would usually remove those small floodplains and restart that process over again. Well, the two-stage ditch design concept was essentially rather than removing those small floodplains, if we need additional capacity so that ditch doesn't flood, can we simply widen out these at the floodplain bench elevation? So that would be the second stage. So that's when we construct a two-stage ditch, that's what we mean. And then kind of a different approach is, well, what if we went ahead and rather than leaving those benches in place, what if we were moving a stream, or we wanted to construct a stream that was wider than the natural trapezoidal ditch that would be there to try and promote a depositional response? Can we trap sediments and nutrients on site so they don't go downstream while we're fixing an issue for the landowner? In this case, it was an urban development. There was an old agricultural ditch down the center that they needed to move to the margin of the property. They were also dealing with a flooding issue, so they wanted to get as much space. So the idea is well, let's build a trapezoidal ditch wider than we normally would. And here's what happens. When water was diverted in, sediment starts to appear. It deposits out. When you have sediments and nutrients in water, you'll typically get vegetation, and that vegetation comes in very quickly. In this case, even after part of a year, you get small, very low floodplains developing, vegetated. We get about the width of a stream we would expect in a natural stream system, but it's just got very low wet floodplains that flood out very frequently. So these little buffer strips that are now on the bottom essentially get to treat a whole watershed's worth of water. You can see that the vegetation grows very quickly, very vigorously. In areas that are low and wet will be wetland vegetation. Areas where deposition has accumulated, you'll get herbaceous vegetation. And a lot of what we measure is how much sediment has deposited there and not gone downstream. So in this particular instance, through a series of ecological successional processes, we're basically letting nature build its own two-stage channel system and trapping all those sediment and nutrients in place as that system builds and creates itself. So we're basically giving nature space to heal itself. That was an urban example. Here's an example in an agricultural landscape. So that self-forming in the foreground was the original trapezoidal ditch that was there. It was essentially given 5 to maybe 7 feet on each side excavated a wider width. You can see what that looks like. Here's a plan form view or an aerial view of that. You can see upstream and downstream as our original trapezoidal ditch. Here's our reach of self-forming channel. So it's wider, definitely, but it largely fit within the buffer strip that was there. And this particular one, it had a small drainage area and a low slope, so it became more wetland in character. And a lot of what we measure is what's being trapped on site, not only how much, but what is it made up of? What's the bulk density? What are the nutrients that are in there? And our colleagues that are experts in wetlands, they get very excited about that soil that they see there and all the good beneficial processes that may go on. And as engineers, one of the things we also do is we want to look at the trade-offs. So how much land is being taken out of production? Have we made the ditch more stable if it was unstable? How does this impact our operations, our crop production, the frequency of flooding, environmental benefits? What is the value of improved water quality, improved habitat? In some agricultural landscapes, these ditches can be some of the best habitat in that entire landscape. Cost in construction, maintenance cost. So we're trying to weigh all of those and give conservationists and engineers tools to weigh those trade-offs. And these are just tools in the toolbox, just like we put a grassed waterway where it belongs, or a wetland where it's appropriate, or drainage water management where it's appropriate. We also want these practices to be implemented where they're help solving landowner problems, but they're also helping water resource problems. So just a tool in the toolbox. And luckily, we have a lot of great folks at the Nature Conservancy, at our soil and water districts locally and statewide, that are very skilled at evaluating the trade-offs and helping landowners understand which tools they can implement to solve these resource concerns that they may have. So just tools in the toolbox. I'm going to share a little bit of the research data we have on this sediment and nutrient deposition, a little bit about our data sets. We've got 9 sites that we've looked at, 9 sites that are kind of in urban and suburban watersheds, 2 sites that we've looked at through our Ohio Department of Higher Ed grants and through Great Lakes Restoration Initiative grants that we partnered with the University of Akron on. The data sets on these are anywhere from 10 to about 16 years. So they're fairly long-term, lots of different weather conditions. So we can start, because of the length of these records, we can have some good confidence, I think, on some of these results. In general, these projects that I'm going to share with you have been fairly small projects, short in length, maybe 150 feet up to 1,600 feet. So just around a quarter of a mile at the top end. So we're not talking huge projects, a range of different slopes. The watershed drainage areas on these projects have been anywhere from 80 to 1,600 acres. So you can see they're treating small watersheds, not like an edge of field practice that might just do a few acres from a field. We are treating larger areas, small watersheds in this case. And if you look at the area that's in treatment, so within the footprint of the conservation ditch that we constructed, relative to its watershed area, it's a very small proportion overall. I know taking land out of production is always a concern of farmers particularly, and that's valid. But overall, it's not large areas. In fact, if you think about what 0.1% might look like, that white dot in the middle of that blue circle is 0.1%. But this practice is usually implemented on an individual farmer's field. So if you think of maybe a 40-acre field and we increase the ditch width by 10 feet over roughly a quarter mile, which would be about a quarter section, 40 acres. That's about 1.5%. So still not a large percentage of the acre. I think where this becomes more difficult for the landowner and one of the barriers to implementation, they think, you know, if I'm going to take somewhere between half an acre and an acre out on that 40-acre field, and land is $8,000 to $12,000 per acre, that might mean somewhere on the order of, you know, $4,000 to $12,000. And that is a meaningful number to a landowner. So that's where, you know, implementing this judiciously, where it helps solves a landowner problem and then also helps address a water quality concern, I think is really important because it does make an impact to that landowner. So a lot of the research measurements that we make are related to ditch morphology or channel form. You can see two examples of projects we've followed over the years, tributary to the Sandusky River and Grant Run. The green dashed line signifies our survey after construction. So after it was constructed, we surveyed it. The black line is the surveyed line after our most recent survey, 10, 12, 13, 16 years later, depending upon the site. So the difference between the green line, dashed line, and the black line is how much deposition has occurred on that site since it was constructed. The red dashed line is what we anticipate that it will grow to someday. So the difference between the black line and the red line is how much additional sediment and nutrients it might store. There are some cases where the existing bed has maybe eroded into the constructed surface. So on some sites, there has been a minor amount of erosion, which we would deduct from the deposition when we're trying to quantify the benefits of this. So really measuring channel form. And a few tables here, if you want to look at the sites where we've made measurements, the rate that the floodplains are building is roughly 2 centimeters per year. We anticipate a lot of these will go on for roughly 4 decades before they're filled up. So although we constructed them at once, they will continue to be a sink for nutrients for multiple decades. And then when we measure the material that's there on site, we take soil samples and we take soil physical properties and soil chemical properties. It looks like the bulk density of these sediments are about 0.8 grams per centimeter cubed. For reference, wetland soils are often 0.5 or 0.6. Upland soils are often 1 to 1.2. If you want to visualize this a little bit better, that density of 0.8 is roughly what flour is. And the amount that it's building per year would be roughly the equivalent to taking this 5-pound bag of flour and spreading it over 2 pieces of legal size paper. So to give you a sense of how deposition is occurring and building up on these sites. If you want to look at how much nutrients have accumulated over time, let's just quickly look at the annual rate. So how much are we trapping per year on these small projects of 150 feet to just over a quarter of a mile? And it looks about like a little over 50 pounds of phosphorus per year. Now recall, the amount we're getting per acre is fairly small, so we're actually accumulating quite a lot in these small reaches. If you look to date, so these projects that are 10 to 16 years old, on average have accumulated about 795 pounds of phosphorus. And if you project out into the future, how much we anticipate that they will accumulate over time, we're going to have plus or minus 3,000 pounds of phosphorus trapped on site. So that kind of gives you a sense of how much is being trapped there. How does this compare to other ecosystems that we think are valuable? So we compared our results to other published values for wetlands. And what we're finding is in our conservation ditches, these small reaches, that the amount of organic matter, carbon, and nitrogen is similar or higher to treatment or forested wetlands, as reported by Bill Mitch and others. And you can see our conservation drainage ditches are oftentimes, we're going anywhere from about 3 grams per meter squared up to almost 25. So our floor is kind of at the ceiling of what has been reported for wetlands. And I think that's largely because we have our small footprints that are treating water from a large, an agricultural watershed. So there's lots of sediment, lots of water. So it's collecting fast within our reaches. So they seem to be very productive, at least here in these initial stages. One of the things that we worry about is how much might be released. If we're trapping nitrogen and phosphorus on site, how much might be released and sent down into the Lake Erie, into the environment. So we've done a lot of looking at nitrogen and phosphorus mineralization. So we use these cores. There's these bags of resin beads that traps what comes in from the overlying water column, what comes in from the groundwater, what's being released from the soil and potentially back into the overlying water column. And then we have 2 check bags. And to make a long story short, what we're finding is even though we're trapping anywhere from about 3 to 25 grams of total phosphorus per year per meter squared, we're only releasing about 0.3 to 1 gram per meter squared per year. And we think there's ways to get that down lower as well. When you compare this to the literature, this mineralization rates, the potential release, are very similar to restored stream systems, swamps, wetlands. So our systems are very much in line with these other valued ecosystems out there. The sediment that we do trap, we're looking at, rather than spoiling it in the buffer, is there a beneficial reuse for that? So can we spread that back on farmers' fields and get some fertilizer or crop production value out of that? So we've done a lot of small plot research. We've looked at the field like a farmer would normally do it, ditch soils, manure, and then subsoil. If you're constructing a ditch, sometimes you generate subsoils, which a farmer may or may not want on their farm field because it's not good soil. So, and we've done these, we've done this over a 2-year crop rotation for corn and soybeans. We harvest that with a plot combine. And here are some of the results. I'm only going to share a little bit of the results with you here. So our control field is just the field that the farm would normally have with no fertilizer. And we did that with fertilizer as well. Sediment is where we dredged the ditch for the deposits that were there. And we did that with and without fertilizer. We did cow manure and then the subsoil. And like I said, the even treatments 2, 4, and 6 had chemical fertilizers applied to them. So what was our control field without any fertilizer? For 5 plots, we did 5 replications of this. We averaged 187 bushels per acre of corn. Where we added chemical fertilizers, those numbers were significantly different. We got about a 25 bushel yield increase. So we did have a yield response to adding chemical fertilizer. But when we added ditch sediment, so this is ditch sediment alone, no chemical fertilizers to it, those numbers were not actually significantly different, but the mean, we got 8 additional bushels of corn when we just spread sediment versus applying chemical fertilizer. So that was an interesting result. This could be a fertilizer alternative. And where we did add sediment with fertilizer, those were not significantly different, but you can see we got about a 20 bushel per yield additional yield benefit by adding fertilizer to the sediment that we applied on the field. And those were statistically different than where we didn't apply fertilizer or applied chemical fertilizers. Lastly, where we applied subsoil, we did get a yield penalty on those, and they were significantly different from where we added fertilizer or sediment plus fertilizer. But interestingly, where we added the subsoil in a thin layer, about roughly 1/2 inch, 100 tons per acre, and we did add chemical fertilizer, we did get our second highest mean yield, which was 230. So perhaps spreading subsoil thinly on an agricultural field will not have a yield impact, and it would actually help reduce the cost of construction of a 2-stage ditch where we're generating the spoil. Where we had soybeans in the second year, I just no-tilled soybeans into these plots again. And I wanted to point out where we added sediment, we averaged about 77 to 78 bushels per acre. And where we had fertilizers or no fertilizers, we averaged less than 70 bushels per acre. So it seems like our sediment soil amendment had at least a 2-year yield advantage, with the means being about 8 bushels different. And that, that's meaningful in terms of crop production because soybeans are fairly expensive now. So we're working on the economics to quantify all the costs to see, does this make economic sense for a farmer to do? Because if it does, at some point they may do this because it's a smart production decision in the future. So really, we need to expand that work. This is one site for 2 years. We need to spread this work, do it in additional sites for additional crop years to really say anything definitively about it. But these are really intriguing and interesting results. Lastly, a couple of management recommendations. To construct a conservation ditch typically costs more money. So can programs like the H2 Ohio program help offset some of those costs for landowners? Some really interesting work going on with tallgrass prairie. Can we put different vegetation types? How do you establish them? And can they promote elevated retention rates? Can we promote more sedimentation, more retention? And there's some great folks doing that work, and that needs to be looked at more. I think we need to have more projects of short to moderate length. I'll just leave that there for now, spreading this across to get the benefits. I think we also want to target these to tributaries that drain to large rivers, because once water and sediment gets into the larger rivers, there's less opportunity for it to be treated. So I think the best bang for our buck is going to where we have ditch tributaries to large rivers. I actually think we need to look at utilization of byproducts. Can we amend the ditch soils with some sort of benign byproduct to help increase the retention rates and decrease the mineralization rates until they can be harvested and moved? And Nick Bosta at Ohio State is doing some of that work, and we're working with them. And I'm hopeful that we continue to support research and technology transfer through our soil and water districts, through the Nature Conservancy and other places to work with landowners so we can have responsible implementation of these projects, because we want to use taxpayers' money wisely. There's a limited amount of it. So I'm hopeful we can continue to do that. And I think at this time I can entertain some brief questions. I'm sorry I went over by a couple minutes here, but I wanted to, here's my contact information if you want to follow up with me afterwards. And I also wanted to recognize Dan Mecklenburg, along with all the other folks that Chung had mentioned before, because he's really collected a lot of this data and helps drive a lot of this research here. So at this point, I'd like to, if there's any questions, I'd be happy to answer those. Everybody's probably taking their after lunch nap.
Thank you, John. It's definitely very interesting, actually. It's so you keep going. I hate to cut it off, but it's a lot of interesting information, actually. It seems like it's kind of like quite a benefit in terms of total phosphate, right? Kind of being retained in the sediments. Do you currently have some results, initial result in terms of like a SRP so far in terms of
right? So all we have today, so there's a little bit of that work out of Indiana. Jennifer Tank has done some water quality sampling with sondes and grab samples. And I think some of the numbers they throw about are maybe 20-25% reduction in SRP. And that's probably after construction. The only thing we have in terms of SRP is we know what the loading to the soil would be, how much mineralization could occur, which is an indicator of potential release, right? It doesn't say that is going to be released, but it could be. And then we are now through the H2 Ohio program, we are instrumenting 4 reaches that where we're going to do water quality monitoring upstream and downstream to see what the changes have been. But right now, our SRP measurements have been limited to those mineralization measurements, and I can only point to some of the stuff that Jennifer Tank has done at some of the Nature Conservancy implemented sites through her work. So I still think there's a number of science questions that need answered, but I think the early results suggest there's going to be a benefit. It's just what's the magnitude of that. We're also doing some soil sampling to say, are there points where we might want to go in and, if we do trap a bunch, right, whether it's from the overlying, through the overlying water column, how does that change through time? So are we reducing more SRP? But at some point, these will become legacy sediments, right? We hear a lot about legacy sediments, and at some point they're going to be saturated. So, but the nice thing about agricultural drainage ditches is they're long, they're linear, and we have a whole industry of folks that can go out and manage these, get those saturated sediments out, and then hopefully return those to the field. So I think there's lots of opportunity for management. We need to discover, what are the right points in time when we go and manage those, because they have become a source versus perhaps a sink of nutrients. And then, I'm just an engineer. We really need some of these folks that are good at biogeochemistry to look more at some of these questions that, you raise related to SRP and the cycling of that in these systems.
By the way, John, I think Matthew Browning has a question. Can you clarify do wetlands and the naturalized channel eventually become a source of nutrient, or do they reach a threshold on how much nutrient they can retain?
Well, I think they can go back and forth between being sources or sinks, depending on how much phosphorus is in the overlying water column.
Mhm.
So, at some point they're going to become saturated. And then, if water quality improves or you have cleaner water coming into the channel, they can potentially release, from my understanding. Like I said, I'm an engineer, not a biogeochemist, but it looks like, at some point, these will become saturated. And if water quality improves, they can become a source, or if they're eroded, then they can, go further downstream as well.
Yeah, I agree. That's kind of a dynamic process, actually.
Yeah.
Does anyone have more questions? I think we're just a little over time. And then,
Like I said,
as John mentioned, John has the contact information over there. And then if you guys have more questions, yeah, please go ahead and then to contact John then.
Well, I see a couple other quick ones here. First of all, it's great to see Laura Fay on here. She was with the Ohio EPA and helped a lot of these projects initially get on and worked hand in hand with Dan. So, Laura, it's great to see you on there. John Blakeman also asks how ditch vegetation factors in. And this is where I think, if you're using these to promote sedimentation and retention, I think anything that provides roughness, so I know that he has some interest in tallgrass prairie, that may help increase sedimentation. As far as uptake and release, I think more measurements need to be made on that. But anything that promotes that, if you look throughout the literature and you're trying to keep phosphorus from going downstream, anything that provides roughness and promotes that sedimentation process, that's really a dominant process, is sedimentation in wetlands and other, floodplain systems. You need that roughness, you need the vegetation to take it up. And then, depending upon the type of vegetation, is that releasing it going downstream, or is it being buried by subsequent layers of sedimentation? I think some of those questions, still need to be answered, but I think they're questions worthy of looking at, more in depth. So vegetation is important for stabilization and promote, encouraging that sedimentation process.
All right, then. If no one have more questions, we're just going to close this out. And thank you very much, John, for being here with us today. And thank everyone for being us with today. And then I hope see you our next Launch and Learn. All right. Thank you. Have a good one.
Thank you.